Okay, today's topic is going to be about the chain rule from Calculus 1. My name is Kurt Overhiser and I'll be your guide as we walk through this topic together. The chain rule is a rule for finding derivatives, just like you've learned the product rule, the quotient rule, and the power rule, except we use the chain rule only when we're dealing with a composition of functions. So you can see that I've written here f of g of x, and f, we refer to it as the outside function, and then g of x as the inside function. In other words, we're putting g of x inside the function f. You remember that from pre-calculus about how to deal with function composition. And the chain rule, as I said before, allows us to find derivatives of such compositions. So I'll go ahead and write down what the rule states that we can use as we look at a few examples. So if we want to take the derivative of a composition of functions, so we want to take the derivative of f of g of x, that is going to be equal to, this is where the chain rule begins now. We say we take the derivative of the outside function, and then we keep the inside function right there. So we take the derivative of f, and then instead of f prime of x, we say f prime of g of x. And then the next part is we're going to multiply it by the derivative of g. And that's what the chain rule says in prime symbol notation. There's an alternative way of writing the chain rule, is if we were to introduce variables for our functions, like if we let y equal the outside function, and then let u equal the inside function, then we can formulate the chain rule using the D notation or the Leibniz notation. And this formulation would say dy over dx is going to be equal to dy over du multiplied by du over dx. And that's another formulation of the chain rule. When we apply the chain rule, we basically do it in two steps. And the first step is to take the derivative of the outside function leaving the inside alone. Step 2 would be to multiply by the derivative of the inside function. Okay, so it's basically a two-step procedure. So let's get our hands dirty with our first example. And what we're going to be doing here is we're going to be looking at the function y equals the sine of x cubed. So the outside function would be the sine function, and then the inside function would be x cubed. In fact, we'll write that down. So step 1 says we take the derivative of the outside function. So I'm going to put y prime for the derivative. And you have to remember that the derivative of sine is cosine. So I'll write that down, cosine. But now, instead of saying the cosine of x, we have to look carefully at what step number 1 says. It says take the derivative of the outside function, which we did, derivative of sine is cosine, but it says leaving the inside alone. The inside function is x cubed, so instead of saying the cosine of x, since we're leaving the inside alone, we have to write the cosine of x cubed. And that's what the first step says. Second step, multiply by the derivative of the inside function. The inside function is x cubed, so its derivative, using the power rule, we bring the 3 out in front, times x, and then we subtract 1 from the exponent, so 3 minus 1 is 2, and we get multiply it by 3x squared. And then just rearranging the terms, or rearranging the factors rather, we get 3x squared times the cosine of x cubed. And then that's the final answer for our first example right there. Okay, on to example 2. With example 2, what we're going to do is we're going to use the same functions, except we're going to switch the order of the composition. So instead of sine being the outside function, it's now going to be the inside function, and then whereas x cubed was the inside function, now becomes the outside function. So I want to take the derivative of the sine of x to the third power, or the sine of x cubed. Okay, since the cubed is the outside function, I have to take step 1. It says take the derivative of the outside function, so I'll do that using the power rule, but remembering to leave the inside alone. So I'll put 3 parentheses squared, because 3 minus 1 is 2. That's where the square comes from. And then to leave the inside alone, since the inside function is the sine function, I have to basically copy and paste the sine function into the parentheses there. And then step 2 says to multiply by the derivative of the inside function. And we just got through saying from the previous example that the derivative of sine is cosine. So then derivative of sine of x would be cosine of x. And then if we just kind of simplify this or just rearrange some of the factors, we get 3 cosine of x times sine squared of x. And then that would be the derivative for number 2. Example 2. Okay, let's go on to another example. Example 3. We could use, let's see, let's look at a semicircle. Y equals the square root of 1 minus x squared. Okay, this is a semicircle with radius 1 centered at the origin that we're trying to find the derivative of, if you remember your conic sections from pre-calculus. And what we're going to do here is use the two-step procedure for taking the derivative. And what we can do here is use the power rule by realizing this is the same as 1 minus x squared to the 1/2 power. And so the derivative, we're going to have to take that 1/2 power, put it in front. So you get 1/2 times 1 minus x squared. And then we have to do 1/2 minus 1, because the power rule for taking derivatives says you, after you bring the coefficient out or the power out in front, you subtract 1 from that power. So that's the derivative of the outside. And then next, the chain rule says we multiply by the derivative of the inside. So the inside is 1 minus x squared. The derivative of 1 is 0. And we subtract from that the derivative of x squared, which would be 2x. So this can be, we can clean this up a bit. If we look at the exponent 1/2 minus 1, we know that that's negative 1/2. So we get 1/2 times 1 minus x squared to the negative 1/2 power times a negative 2x. And then we can see that since we're multiplying, the 2's will cancel multiplicatively. And so what we end up with is a negative x times 1 minus x squared to the negative 1/2 power. And if you remember from algebra, when you have a negative power, you can make that power positive by putting it into the denominator. So we could do this. We could say negative x divided by 1 minus x squared to the positive 1/2 power. And then realizing that the positive 1/2 power is the same as the square root, so you get negative x divided by the square root of 1 minus x squared. And then that is our final answer for example 3. On to example 4. With example 4, we're going to be looking at the function y equals the tangent of the sine of the square root of 1 minus x squared. And we want to take the derivative of this. This looks like a formidable function, only in that it has more than one function composition associated with it. You can use the chain rule not just for one function inside of another function, but you can use the chain rule when you have one function inside another function, inside another function, inside another function. You can think of it as like the layers of an onion that you can kind of peel away. You start off with the outermost layer of the onion, you peel that off, and then you start to peel all the other layers of the onion until you get to the core of the onion, which would be the innermost function. So if you look at what I've just written down, the function, the tangent of the sine of the square root of 1 minus x squared, the tangent would be the outermost function. And then once you peel that layer off, you get to the sine function. You can peel that off, and then you get to the square root function. And then peel that off, and then you get to the inner core of the function, which would be the 1 minus x squared. So to show you how we would use the chain rule in this situation, we just start using the onion analogy, where you start from the outside and work your way towards the inside. So the derivative, we start off with the derivative of the tangent, which you have to remember is secant squared. So we take secant squared, and then remember it says to leave the inside alone. So the inside in this case would be the sine of the square root of 1 minus x squared. So you copy and paste that, put that there, and then the chain rule says we multiply it by the derivative of the next layer of the onion. And we've already dealt now with the tangent, so now we have to deal with the sine function, and its derivative would be cosine. And then we have to figure out what we're going to take the cosine of, and that's going to be the same thing that we're taking the sine of. It's going to be the square root of 1 minus x squared. And we're still not done, because we've addressed the tangent and the sine, but we still have to use or multiply it by the derivative of the square root of 1 minus x squared, which from example 3 we know what the derivative of the square root of 1 minus x squared is. It was negative x divided by the square root of 1 minus x squared. So I put parentheses here and then write negative x divided by the square root of 1 minus x squared. And then that would take the derivative, that would take care of the innermost function. So you can see that we've got three functions composed one inside of the other. And so we've got this part here, the secant squared of the sine of the square root of 1 minus x squared, that takes care of the first layer of the onion, the tangent, the outermost layer. And then we have this middle part right here, the cosine of the square root of 1 minus x squared. That's for the middle layer of the onion, which was the sine. And then the innermost, the core of the onion, the square root of 1 minus x squared, it corresponds with this part right here, which we addressed in the previous example, example 3. So this is just to show you how to use the chain rule, and I hope you learned something here today that you can take with you in your studies as you go through the calculus sequence. And good luck in your studies, and take care. Bye-bye.